All right, so let's talk, actually today is going to be more physics-based than chemistry-based, which is good. So here's the basic idea. When you look at the structure of an atom, and this is what we're going to be talking about for like today and tomorrow. By the way, if you want to plan ahead, we're going to have a midterm final a week from tomorrow. Okay? So, what? It's not going to be that much different than that last test that you took that had mole conversions, gas laws, and now we're going to have structure of the atom on it. So, there isn't all that much more that's going to be on it. Okay. So, you've got three big players on any structure of the atom. You got protons, neutrons, okay? And these are these big lumpy particles that are held in the nucleus, okay? So here's the dichotomy between the nucleus and the structure of the atom and how everything fits together. So the protons and the neutrons are held together in an incredibly dense nucleus, okay? They occupy a very, 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 very small percentage of the volume, but they contain 99.9% of the mass. So you would think that it would kind of like go hand in hand, like, oh, okay, well, if that contains a lot of the mass, that should produce a lot of the volume. Okay, it works the exact opposite. So electrons. So here's like this nucleus. And then you've got these electrons that are moving around. So one analogy is that if you've ever been out like in the garden and you have like say a cantaloupe, okay? So the cantaloupe is like the nucleus. And then the mosquitoes that are like, or gnats that are flying around, those are like the electrons. But these gnats or electrons are moving at close to the speed of light. So what you see is this perception of like an electron cloud. What appears to give us volume is these little gnats are moving at close to the speed of light. And so that's what gives it volume, because they're just moving so fast. So when you look at how we represent this, and again, this is like counterintuitive. Everybody thought, oh, the plum pudding model, that was cool because the positive and negative charges were balanced out. Turns out that was a train wreck. Rutherford did that, shot the alpha particles. And now I can talk about what alpha particle is, and now you know what this is. So what he did is he had a radioactive source of thorium. And the alpha particle that he shot out, he didn't even know what it was. That's why he called it an alpha particle. What it turned out, and let's see if you all can handle this. This is the actual structure of an alpha particle. So if I told you, if I wrote this symbol, okay? What can you conclude? You can conclude a lot from that symbol. So what can you figure out? Tell me one thing that you can figure out. Keith.
There's 2 neutrons in it.
There's what?
2 neutrons.
How do you know?
There's the 2 protons on the bottom, and then 4, the mass number on top.
Fantastic. So what do we call that value of 4?
Mass number. Mass
number. Okay? So the mass number is the total number of nucleons. Okay? So we've got down here, Grace, what's this bottom number?
The mass number?
Nope.
No, the atomic number.
The atomic number.
Protons.
And what does the atomic number tell you, Grace?
Protons.
Okay, so this is the number of protons. And this is the total number of protons and neutrons. So, Ella, what does that 2 plus tell you?
Charge.
Positive or negative? Do not make this difficult.
Well, isn't it the opposite?
No. All I'm asking is what is the charge on the particle?
Positive.
Positive. Okay. Now, because it's positive, does that mean have we lost 2 electrons or gained 2 electrons?
Loss.
Okay. So a typical helium atom. Okay. You go to a party and someone's got a helium-filled balloon. So a typical helium atom has 2 protons, 2 neutrons, and 2 electrons. Okay? They're buzzing around. It's very stable. We'll get into why it's stable later on. And so for a long time, we didn't even know the element helium existed. So if you look at the origins of the word helium, and we'll talk more about spectrums later. So the first place they actually found helium was they were analyzing the light that was emitted from the sun. So the word helium comes from the Greek word helios, which means sun. And so we didn't even know the element helium existed, mainly because it's not very abundant and it doesn't react with anything. So helium is just kind of this rare, very rare gas. But it's cool because it's lighter than air and it doesn't react with anything. So that's why you use it in balloons. So a typical helium atom is going to have 2 protons, 2 neutrons, 2 electrons. So what happens in this radioactive decay is that this big massive nucleus splits apart and it kicks out what Rutherford called an alpha particle. Because again, we didn't even know the element helium existed. It wasn't until later on that they figured out, oh, this is just the nucleus of a helium atom. So these particles, this is going to be important, particles were positively charged because their electrons were stripped off. So he soldered out the gold foil, it ran into a positively charged nucleus, every once in a while it would hit, boom, and it would bounce straight back. So that's how they figured out that the nucleus was very massive and positively charged. So what we're trying to figure out is, okay, how do we represent this? So later on, they figured out that there were isotopes. And so when you have an isotope, and this is kind of these questions, when you get into this, like over here on page, on page 9, okay? So since we're talking about the structure of an atom, actually, let's go to page 8. Flip over to page 8, because this is what you all should have filled in, is this page 8. This is worth a lot of points. So let's make sure that I'm going to work through some of these, make sure you've got what I want. So if you go down there to like, I don't know, like you've given you sodium and then a dash 22. Okay, so this is like a secret code, okay? And it's like, and once you're in the chemistry club, then you go, oh, I know how to read this code. So you have sodium dash 22. So there's a couple of reasons why you write these isotopes in different ways. One is just the act of typing, okay? So for years, it was very difficult to do subscripts, superscripts at the same time, okay? Even now, I have to have a special program. If I wanted to do like a nuclear symbol, it's tough to do. Like, I can't just do your basic word functions. I have to have like a specific program to type that in. But I can easily type sodium dash 22. Okay, it's simple. But the problem is it doesn't convey very much information. I'm limited. I can't put the atomic number there. I can't put if there's a charge. The only thing I can tell you is that, hey, I'm dealing with sodium 22. Okay, that's all I can do. So if you go across in that line, then the next column they say, oh, that's Na 22, and then a 1 plus. Okay, so again, in this situation, and if there's any information that you kind of leave off, typically what they don't put is the atomic number down below, mainly because there's no variation on the atomic number. Addie, what's the atomic number of sodium?
11.
11, okay? So every sodium atom, and this is going to be important, every sodium atom that exists has 11 protons. We can change the number of electrons, we can change the number of neutrons. So one of the most important things you have to remember, that it is only the number of protons that determines the type of atom that it is. It isn't the number of neutrons, it isn't the number of electrons, it is solely the number of protons. So any atom, regardless of neutrons, regardless of electrons, doesn't make any difference. The only thing that matters in terms of the type of atom is the number of protons, nothing else. It's that atomic number. That is the whole key. But the problem is, everybody says, oh, well, let's just make gold. You know, we'll just chunk a bunch of protons together, and then we'll have gold. How difficult can this be? You know, why is there a shortage of gold? Well, here's the problem, is that it's a double-edged sword. The nuclei of atoms is very, very stable. What that means, the other side of that, is that it's very difficult to change that number of protons. Okay, and you get into something called binding energy. Binding energy is how much force it takes to basically build an atom, and it's a very, very large number. And so this is why we can't solve the problem of, well, we need more gold. Okay, cool. Let's chunk some protons together. It doesn't work that way, mainly because there's so much energy involved in that process. Okay, so you have the Na1 plus, so here's what I'm looking for. So if you go across those columns, you've got the atomic number, which is just going to be 11. Your mass number, in this case, is going to be 22. That's a horrible mass number. Okay, and then you've got number of neutrons. So here's the deal. So if the mass number is 22 and the atomic number is 11, Peyton, how many neutrons are there?
There's going to be 10 neutrons. Or not 10 neutrons. Sorry, 11.
11 neutrons, okay? So there's going to be 11 neutrons, okay? You got to the next column.
Yeah.
So now, on the number of electrons, and this is something that Ella mentioned before, here's the dichotomy when you're talking about charge. A positive charge means that you've lost electrons, okay? So the number of electrons here is going to be 10, and then on that charge over there, you're going to put 1 plus, okay? So that's what I'm looking for. When you get into isotopes, so down there towards about in the middle, you have carbon 12, carbon 13, and carbon 14, okay? So here's the deal, and this will play out more later on. So each proton and each neutron, and when we talked about, remember we talked about like relative atomic mass. The relative atomic mass of carbon is 12, hydrogen is 1, oxygen is 16. So as a crude approximation, each proton and each neutron has a relative atomic mass of about 1, okay? It's a little bit more than that, but it's pretty close. So as an approximation, you can say each proton, each neutron has a relative atomic mass of about 1. So what you see on the periodic table is an average value of all the isotopes that exist, okay? So now keeping that in mind, so pretend that you don't know anything about this, okay? You don't know anything about this, okay? We have not had this discussion at all. You know nothing about this. And I say, all right, class, I gave 1,000 kids a quiz, okay? And there were 3 possible scores on the quiz. A score of 12, a score of 13, and a score of 14, okay? And if I tell you that I took the average of 1,000 scores, and those are the only 3 possible scores, 12, 13, or 14, and I take the average score, I say the average score was 12.01. So I gave this quiz to 1,000 kids, and the average score was 12.01. Which score do you think occurred most often? Mr. Grove?
12.
12, okay? You got to figure the vast majority of the kids got a score of 12. Now, if I said the average score was 14, then you'd say, oh, probably about everybody most people got 14. So, now keep that in mind. So when you look at the relative atomic mass of carbon, which is listed as 12.0, which isotope do you think occurs most often in the universe? Carbon 12, carbon 13, or carbon 14? Mr. Peterman.
Carbon 12.
Yeah. So the vast majority of carbon that makes up you, okay? Your DNA, when you breathe in carbon dioxide, there's carbon that makes up your cells, all of that. The vast majority of that is carbon 12, okay? There's very little carbon 13, there's very little carbon 14. Same thing when you look at hydrogen, okay? There's 3 isotopes of hydrogen. There's hydrogen 1, hydrogen 2, hydrogen 3. Okay? So, which isotope do you think occurs most often? Hydrogen 1, hydrogen 2, hydrogen 3. Miles.
I don't know.
Okay.
Sorry, I was doing this.
Right up. I'm going to save you. Okay? Maybe your eyesight's better than mine, or you can look on your periodic table. What's the relative atomic mass of hydrogen?
1.
1.00. Okay? So which isotope of hydrogen do you think occurs most often? Hydrogen 1, hydrogen 2, or hydrogen 3?
1.
There you go. Okay? There you go. And most of the time they're like whole numbers, but some of them, like chlorine is 35.5. So chlorine kind of has two isotopes of relative abundance, chlorine 35, chlorine 37. And so those actually kind of have pretty equal abundances, and that's why sometimes these are like, these aren't whole numbers. So when you look at the periodic table and you look at that relative atomic mass, you can't figure out exactly which isotope it is, but you can figure out probably on average which isotope occurs most often, okay? So like if you look at lithium, okay? Relative atomic mass of lithium is like 6.99, okay? Call it 7. So what that means is that your typical lithium atom is going to have 3 protons and 4 neutrons. Oxygen is 16. Most of those have 8 protons, 8 neutrons, okay? So when you look at the relative atomic mass, keeping in mind that each proton and each neutron is about 1. Technically, there's a little bit difference, but that isn't important until you get into some really calculations involving Einstein's theory of relativity. So in round numbers, for this class, you can say a proton and a neutron has a relative atomic mass of 1. So when you look at that relative atomic mass, you can get an idea, okay, what's going on? Hydrogen is 1. Okay, most abundant hydrogen isotope is hydrogen 1. Oxygen is 16. Oh, probably the most abundant isotope is oxygen 16. Okay, so decimals get a little bit crazy because there's a whole bunch of different isotopes, but at least you can get an idea of what's happening with those isotopes based upon the fact that it's an average. Okay, so when you get down to, like, for example, that one towards the bottom, because this is probably one of the more difficult ones. So you have 70 gallium 3+. And then right above that you had, and so let's make sure everybody's cool with what I want. And then above that you had gallium 70. So what's the difference between gallium 70 with 3+? Now, I'm going to ask you this question, okay? There's 2 ways that you can create an atom or an ion with a charge of 3+. Option number 1, you can lose 3 electrons, okay? That's an option. You can lose 3 electrons. Option number 2, you could gain 3 positive charges. Okay, so those are the 2 ways I could create an ion with a charge of 3+. I could lose 3 electrons and keep the same number of protons, or I could keep the same number of electrons and gain 3 protons. Okay? Izzy, which way did this go? When I went from gallium to gallium 3+, did I gain 3 protons, or did I lose 3 electrons?
You lost 3 electrons.
How do you know I didn't gain 3 protons?
Because it's still gallium.
Fantastic. This is why, listen to me, okay? This is why you never form ions by gaining or losing protons, okay? Number 1, it's incredibly difficult to do because the nucleus is so stable. Number 2, if you gain or lose protons, what are you changing? You're changing the element because then you're changing the atomic number. So this is why you never, I repeat, never, create an ion by changing the number of protons. Because as soon as you change the number of protons, you change the atomic number, and you change that type of atom. Okay? Remember that. Okay. So, you go across, you got gallium 70. How are you going to figure out, Izzy, how many protons are in the nucleus of gallium?
How do I figure it out, or do you want me to tell you how many are in there?
Either one. Actually, let's do both.
Alright, you can figure it out by the periodic table
Okay?
and 31,
Okay? How do you know?
because the periodic table.
Periodic table says so. Okay? So now, let me tell you how I handled this. Okay? When I was filling this out, I don't remember exactly where gallium is on the periodic table. So I cheated a little bit. So let me see your periodic table. So I knew it was gallium 70. So to figure out where gallium was, instead of spending a lot of time going through the periodic table, I looked at that 70, and then I went across and found gallium based upon the fact that I found the relative atomic mass of gallium is like 69 point something. So if you know which isotope that you have, and you know the mass number, and you're trying to figure out what's the atomic number, look on your periodic table. You come across and go, oh, gallium, yeah, that's 69.7. So what that tells me, again, since that relative atomic mass is 69.7 of gallium, the most abundant isotope of gallium is probably gallium 70. There has to be something a little bit less than that, because the average is 69.7. So there might be like some gallium 69 or gallium 68, okay, because that average is a little bit less than 70. But I got to figure the most abundant isotope is gallium 70. So if you can't find, and you don't know where an element is on the periodic table, but if you know its mass number, you can find it that way by looking across and finding it that way. So now gallium is kind of cool, because gallium actually it's a silverish metal, but the melting point of gallium is pretty close to the body temperature of human beings. So if you have gallium and you hold it in, it's solid. But so if it's sitting out here, gallium is very, very rare. But if it's sitting out on the table, it's a solid. But if you grab gallium and you hold it in your hand, it actually gets warm enough that it will turn into a liquid. So gallium is a pretty cool element. Okay, so I've got, each of these both have 31 protons. Cool with that, right? We're solid. So when I have that charge of 3 plus, how many electrons does that 3 plus gallium atom have? Ethan?
28.
Fantastic. So I got 28 electrons. Now, some people like this analogy with it's like a dance, okay? So initially at this dance, imagine that you're in middle school, okay? Do you still have dances in middle school?
Yeah.
Okay. Okay, always awkward, all right? But let's say there is no way to be cool at a middle school dance. So let's say that you have 31 guys, okay, on one side. And on the other side, you have 31 girls, okay? And girls tend to be more positive, so we're going to make them positive, okay? They're excited to be there. Oh, right. Guys, they're a little bit more surly. They're trying to be cool, so they want to be over here and be negative, okay? So as long as the number of guys equals the number of girls, everything is neutral, okay? I'm not saying there aren't positive charges. I'm not saying there aren't negative charges. But overall, everything is neutral, okay? So what happens then is that we can't, here's the rule, we can't change the number of girls that are at the party. Okay, we have 31 girls, that's it. Boom, we have 31 girls, that's all we can do. Okay, if we're at the gallium party, there can only be 31 girls. If we change the number of girls, we change the name of the party. Guys, they're squirrely, we don't care, especially middle school boys. They just smell like, they bathed in cologne anyway, and they're just weird. This is why I don't teach them in middle school, God forbid. I did my student teaching at Fort Riley Junior High, out by Junction City. Swear to God, I would never set foot in the junior high again, and never have. So, you got 31 girls, 31 guys. It's neutral. So at this point, what we're saying is that 3 of these guys decide, hey, I'm too cool for this. I'm going to call up mom, and I'm going to have her pick us up, okay, because you're in middle school. You can't drive. It's like, oh, cool. I'll call mom, right? So, 3 guys leave. Now you have an abundance of girls, so you have 3 more girls. Then you have guys, hey, the party goes positive, there you go. That's one way to think about it. So some people like a dance analogy. As long as the number of girls equals the number of guys, it's neutral. You can't change the number of girls, you can only change the number of guys. So if 3 extra guys show up, oh, guess what? Now that the mood turns negative, girls are going, oh, great, there's even more guys now, and it automatically turns negative. Because the girls are going, great, we have more middle school boys. That's horrible, okay? And literally the mood just goes negative. Okay, got that. Everybody, any questions on that big chart on page 8? Got it? Good? Fantastic. Okay, so let's talk about these questions on number, over here on page 9. At this point, you should have no trouble answering those questions on page 9. So, but let's make sure everybody's cool. Question number 1 says, how many protons are found in each of these following hydrogens? So, this is what we're going to talk about. So you have your basic hydrogen, which is hydrogen 1,1, and then you have, okay? So you have your normal hydrogen, and then you have, this is what's called deuterium, and then you have this, which is called tritium, okay? Tritium comes from the Greek word tri, there's 3, it has a mass number of 3. So these, do you think, okay, looking at the relative atomic mass of hydrogen, do you think deuterium and tritium are pretty abundant, or do you think they're pretty rare? Miles?
Abundant?
Miles, I want to do a quiz. Okay? There's 3 possible scores on the quiz. 1, 2,
Okay.
and 3. I'm going to take the average score of 1,000 kids.
Mm-hmm.
The average score is 1.00.
Mm-hmm. 1. So, rare.
Rare. Okay? Now, the only place you can find deuterium and tritium is actually, there's a lot of it in ocean water. Okay? It's still bound up in water, but that's one of the possible things. It's called heavy water, mainly because of the fact that it has more neutrons in it. Okay? And you can actually use that as a radioactive source. So, that's a whole other discussion. So, on question number 1, Miles,
Yeah.
how many protons are found in each of the following?
1.
1. Okay, don't miss it. It's 1. That's all you got. It's just 1. Okay. Now, how many neutrons are found? So in this one, Miles, how many neutrons are there?
0.
Hold on. Yeah. Okay, all right, thank you. Bye-bye. Miles, you have to leave at 8:40.
Yeah. Oh, I thought it was 8:45. My
So
bad.
I know, but they called and that's why.
Okay.
Okay, so here's the deal. So every one of these has 1 proton, right? This is the only element, this is what makes this unique, okay? Hydrogen is the only element that, for the most part, except for deuterium and tritium, that has no neutrons, okay? You look at helium, lithium, sodium. Every other element to have a stable nucleus requires neutrons, okay? So this is what makes hydrogen 1 unique. It's the only element that does not have a neutron, okay? You're going to have different isotopes, but they're very, very rare, okay? So that's what makes that unique. So what that means is that from a cosmological viewpoint, when the universe was formed right after the Big Bang, the universe basically decided, hey, what kind of particles are we going to make? So the universe could have just made electrons. We wouldn't be here having this discussion because everything would be negatively charged. The universe just didn't make positively charged particles because we wouldn't be here talking about this. And even if the universe had just made positive and negative charges, okay, let's say the universe says, you know, I just want to make 2 kinds of particles. I just want to make protons, and I just want to make electrons, okay? And that's all it made. We would not be here having this discussion because without neutrons, you couldn't have the more complex atoms. You could not have carbon. You could not have oxygen. You could not have iron. So and everybody says, what's the big deal about neutrons? Without neutrons, the universe as we know it would not exist, because you couldn't even build helium, okay? Because the neutrons have to be there to stabilize that nucleus. So it's a good thing the universe decided to make neutrons, because without neutrons, you could not, the only thing you could ever have was like hydrogen. Okay, well that's exciting. Okay, great, we'll have hydrogen. You can't build tables, squirrels, Oreos, anything like that. Okay, now, so when you get to the electrons, okay, Emma, how many electrons are in each one of those?
Electrons?
Electrons.
1.
One, okay, how do you know?
Because
What's missing from each of these symbols?
the charge.
Yeah, there's no charge, okay? Because for lack of a charge, you just have to assume the number of electrons equals the number of protons. Okay, so we get to question number 4. What structural characteristics do all hydrogens have in common? Okay, when they're talking about structural characteristics, okay, basically what they're asking for is what's happening in terms of the particles. Okay, so structural characteristics is a big fancy way of saying what do they have in common in terms of their particles. So all you have to say is that on number 4, they have the same number of protons, and then the same thing on number 5. What structural characteristics do all carbon atoms have in common? They have 6 protons. Okay, so do not make that question complicated. Now, when you get to question number 6 on the top of page 10, okay. So let's talk about this. It says, what does the mass number tell you? Okay, now here's what I want you to see, and this is one of the most important differences that you have to look at. Is that the mass number itself will always be an integer, okay? The mass number is never, ever a decimal, okay? It's never a decimal. You're not going to have a mass number of 32.8, okay? Because it's like the whole number. So if I said, hey, somebody comes in and says, hey, how many kids do you have in your room? I got 15, okay? I'm not going to say, how many kids do you have in your room? I got 13.2, okay? No, right? I have a whole number of students. Now, within that, I might have 7 guys, 7 girls, but in terms of the numbers, that's always going to be a whole number. So you will never, ever, ever, ever see a mass number as a decimal, because it's a whole number of particles, okay? Now, the next question is a little bit tricky. It says, can you find the mass number of an element on the periodic table? Okay? Yes and no. Okay? And here's the reason why. So this is what we talked about. You looked at hydrogen, and the relative atomic mass of hydrogen is 1.00. Okay? So as Miles figured out, he goes, oh yeah, there's 3 different isotopes of hydrogen. There's hydrogen 1, there's deuterium, there's tritium. Okay? But the vast majority of hydrogen is just hydrogen 1, because what you see on the periodic table, okay, listen to me, what you see on the periodic table is an average, okay? So when you look at that relative atomic mass of hydrogen being 1.00, that isn't the atomic number. Excuse me, it isn't the mass number. But you can figure out that most isotopes of hydrogen are just hydrogen 1, okay? You look at helium. What's the relative atomic mass of helium? Grace, what's the relative atomic mass of helium?
2.
No. The relative atomic mass of helium. You gave me the atomic number. 4, okay? So if you look at helium, that's 4.00. So that's technically not the mass number, but you got to figure that what's the mass number of the most abundant isotope of helium? 4. Okay, so you can't necessarily figure it out, but you can get a pretty good idea of what that is. So that's why that answer is technically yes and no. It's like, no, you can't figure out the exact number, but if you look at it, that it's an average, you can get an idea of which isotope is most abundant, okay? Now, where it gets weird is you get like iron. If you look at iron, that's like 55.5, okay? Especially ones that have like middle decimals, like, whoa, 55.8, 35.5 with thorium, things like that. That means that there's quite a few different isotopes, and there isn't one that's really dominant. So, like I said, you can't figure it out, but you can actually figure out a pretty decent amount of information, because each proton and each neutron has a relative atomic mass of about 1, okay? And that's why you can use the relative atomic mass to get an idea, but you can't necessarily know the exact number, okay? Does that make sense? Good? Got it? Okay. So you should be able to answer question 8 and 9. So isotope, all you have to say is something like, there's different ways you can answer question number 8 on page 10. You can say isotopes have the same atomic number, but they have a different mass number. You can say they have the same number of protons, they have a different number of neutrons. You could say they have the same number, this is kind of the technical term, you could say they have the same number of protons, but a different number of nucleons. Okay, and nucleons are just a generic term for protons and neutrons because they're in the nucleus. Okay? Got that? Good? Any questions up through there? Okay, now let's start talking about this concept of ions. Okay? So, up there at the top, kind of about part of the way down. Actually, y'all have been sitting. Stop that camera for a second. Stand. Okay. So, now we need to have a brief physics discussion. Okay? So, one of the problems that they ran into was that how do you determine the mass of a proton or an electron? Okay? Because they're incredibly small values. So, from a historical perspective, this is in late 19 teens, like 1918, 1920, that type, about 100 years ago, okay? So they figured out that there were electrons, okay? So J.J. Thomson figured out the structure that there were electrons. Rutherford then came along and shot the alpha particles. These are physicists, these are all physicists. They said, okay, the nucleus is very dense, it's positively charged. That created a problem because the protons should repel each other. And so then they said, okay, well, how do you find the mass of an electron? Okay, how do you find the mass of a proton? It isn't like, hey, let's figure out what a Chick-fil-A sandwich weighs. Okay, we'll grab it, we'll put it on a scale. Boom, it weighs a certain number of pounds or grams or kilograms, something like that. But when you're dealing with subatomic particles, we can't grab an electron with a pair of tweezers and go, oh, there's an electron. Grab it, put it on a scale, and go, oh, here's the mass of an electron. Okay? Because it's so incredibly small. So the short version of what they did is that they took like a positive and negative plate like on a battery, okay? And what they did is they made these particles travel through these plates, and then they would subject them to a magnetic field, okay? And when these particles would go through a magnetic field, particles that are charged, when you interact with a magnetic field, they change direction, okay? So to kind of get a nice, let me go stop that for a second. So this is something known as ferrofluid. It's like mineral oil, and then it's got very, very fine suspended iron within it. And this is just your basic magnet. And so when you put this near it, what you'll see is that it affects these particles. And what you'll see is that it actually makes like little spikes, okay? And as you get closer to, as that magnet gets closer, the spikes become you see a lot more spikes and they become much more condensed and finely pointed. As you pull it away, they actually spread out. So what that tells us is that the force from a magnet, that magnetic field, isn't a continuum force. That force actually exists in what we call magnetic field lines. And so the reason that that exists as spikes is because of the fact that a magnetic field isn't continuous like gravity. Gravity is a continuous field. Magnetic field magnets actually exist in individual lines, which is why when you do this, you see these spikes. So when particles interact, charged particles, electrons and protons, when they interact with a magnetic field, they change direction, okay? It makes them travel in circular paths. So what they did is they basically said, okay, we're going to shoot these particles through here, and then they're going to hit this magnetic field. And when they hit this magnetic field, they're going to change direction. They're going to travel in a circle. And so what they saw is that depending upon if it's a positive or negative charge, some of them, the positive charges would go in one direction. The negative charged particles would go in the opposite direction because they're opposite in how they interact with the magnetic field. And then also where the particles would land would tell them the mass of the particle. Okay, it's a hugely complex calculation, but it was kind of like, here's the best analogy that I can give. So if I swing this rubber stopper around over my head, okay, that takes a certain amount of force. If I were to take this bowling ball and swing it over my head, that would be a completely different amount of force, okay? So what they figured out is that they would measure where these particles would land, so they would have sensors that would detect where these particles were going. And then, so the protons, the positively charged particles would go in one direction. The electrons would go in the opposite direction. And if you know where they land, you can solve for the mass. And like I said, it's horribly complex. If you take AP Chemistry or AP Physics, that's one of the things you will do is we'll go through and we'll figure out, we'll actually do these calculations like how do you find the mass of an electron? So you can't measure it directly. So what you do is you send it through an electric field and a magnetic field, and then where it lands, you can work backwards and figure out what the mass. So I'll pass this around, okay? And this is going to be important. And it's going to talk about these coulombic forces I'm going to talk about next. Is that the closer it is, the stronger the field. The further it is, the weaker the field. So you can do it like this, okay? There's a couple of different ways you can do this. You can do it on the side, whatever. Okay, so I'll pass this around. It's just fun to play with. So, and if you're looking, if that absolutely says, wow, that speaks to me, then ask Mom, you can buy it on Amazon. Just do a search for ferrofluid, and it's just cool. Okay, so here's the deal. When you look at these numbers, so here's the mass, and you've got to understand these different units. So 1 atomic mass unit, okay, because again, atomic mass units is what they had first, okay? Because when they were starting to figure out relative atomic mass, they did not have the technology to measure the mass of a single electron or a single proton, okay? Didn't have the capacity. Later on, once we developed, oh, here's magnetic fields, electric fields, and sensors that can pick up where these are, then we could work backwards. So what they knew first was the value of relative atomic mass. So conveniently, it worked out that 1 atomic mass unit was basically the mass of a proton, and 1 atomic mass unit was also the mass of a neutron. So I'm never going to expect you to know these, but this is what I want you to see. So 1 atomic mass unit, and this is one of the things that they've got listed here on the middle of page 10. Okay, this is just the number that they gave you. So 1 atomic mass unit, and it varies depending on if it's a proton or a neutron, is about 1.66 times 10 to the negative 24th kilograms. So, or grams. In physics, we work off of kilograms. So, here's what I want you to see. The mass of a proton or neutron is 10 to the negative 27. The mass of an electron is 10 to the negative 31st. So what that means is, in round numbers, the mass of a proton or neutron is about 1,860 times greater than the mass of an electron. Okay? So, relatively speaking, electrons are very, 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 very small, okay, relative to the mass of a proton. So what that means is, if you had a scale, like a pan balance, remember we did that with the eggs, okay? So what this means, if you were to set up like a pan balance, and if you were to put one proton or one neutron on one side of it, it would take you about, you'd have to stack about 1,860 electrons on the other side to balance that out, okay? So protons relative to electrons are very, very massive, okay? But, and this is going to be this is the other thing that we need to talk about today. The other thing that happens, though, is that they both contain the same amount of charge, okay? So in science, you talk about the amount of charge in a unit called a coulomb, okay? It's called a Coulombic force. So all electrons, and this is the cool thing about the universe that we're in, is that every electron that we have ever studied, the universe is like the ultimate factory in terms of cranking out things. Every electron, every proton, every neutron that we've ever studied, they have two things in common. They all have the exact same amount of charge, and they all have the exact amount of mass, okay? There is no variance, okay? It isn't like, oh, some electrons are heavier than other electrons, or some protons are heavier than other protons, or some protons have more charge than other protons do, or some electrons have more charge than other electrons. It is our universe did an amazing job of cranking out particles that all have the exact same amount of charge, and they all have the exact same amount of mass, okay? It's an amazing thing. So, the universe said, we're going to make electrons. Tiny, 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 tiny bits of matter. They all have the same amount of charge. It's negative. Protons, much, 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 much more massive, but all protons have the same amount of charge as an electron does. So this is going to be important. Because initially they thought, protons are much more massive. Because they have more mass, they should have more charge than the electron does. Because I said, is there a correlation between charge and mass? Protons are more massive. Do those have more charge? And they figured out, no, they don't. So that was one of the things they struggled with. It was like, man, these protons are massive. But they have the exact same amount of charge as the electrons do. It's like, that's kind of weird, okay? And then you got neutrons, and they're cool, okay? They're just there. They have no charge at all, but they basically have the same mass as a proton does. So the subatomic world is incredibly strange, okay? It's just weird. It works, but it's just a little bit weird. Okay, so here's what you've got. On this page down here, okay, this kind of the bottom of page 10. So let's go through this, make sure everybody's cool. So what's the structural difference between an atom and an ion? So here's the deal. Everything that we're going to study from here on out is one of two things. All the particles we're going to talk about are going to either be atoms, where the number of protons is equal to the number of electrons, or we're going to have ions, and within the ions you can have two types of ions. You can have cations, and you can have anions, okay? So if it's a cation, that means you have a greater number of positive charges than you do negative charges. If it's an anion, the number of negative charges is more than the number of positive charges. Okay, that's it. So literally, everything that we're going to talk about is either going to be an atom or an ion. Okay? That's it. If it's an ion, you have one of two situations. You have more electrons than protons, that has a negative charge. If you have more protons than electrons, it's a cation. Okay? That's it. So, there you go. So, on number 10, it says, what's the structural difference between an atom and an anion? Basically, the number of protons doesn't equal the number of electrons. Now, on number 11, it says in atomic mass units, what's the mass of an electron? I'm just going to give you this number. You can Google it. I'm just going to save you some time. But one electron, and here's the difference. One electron has a relative in atomic mass units of 0.000548 AMUs, or if you like scientific notation, it's 5.48 times 10 to the negative fourth AMUs. Okay? So, the only I'm never going to expect you to have that number memorized, okay? But here's what I am going to expect you to know. Oh, each proton and each neutron has a relative atomic mass of 1. Okay, they're massive. Each electron has a relative atomic mass of 5.48 times 10 to the negative 4. So all I want you to know is that electrons are tiny, 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 tiny bits of matter. So electrons do two things. They allow atoms to bond together, and they create space. Protons and neutrons create the positive charge, and they create mass. So space, the space that you exist, is created by your electrons. The mass that you have is created by the protons and the neutrons. Okay? Electrons do contribute a little bit of mass, but relatively speaking, it's such a very, very small amount. So we exist because electrons create space and they bond together. We have mass because we have protons and neutrons. Okay? Got that. So, then on number 13, it says protons and neutrons have the same mass. What is the approximate mass of a proton and neutron in atomic mass units? Okay? Do not make this difficult. It's just 1. Okay? The answer to 13 is 1.0. Do not make this difficult. Now, let's talk about question 14. So you're given 2 bits of information here. So you carbon 14, and they're told that is about 14 AMUs. Okay. So does this agree with what you determined in questions 11 and 13? Here's the whole point. Okay. Protons and neutrons have a relative atomic mass of about 1. Carbon 14 has, oddly enough, a total of 14 protons and neutrons. So therefore, because each proton and neutron has a relative atomic mass of 1, therefore the relative atomic mass of this atom is also 14. Okay? So do not make 14 difficult. It's the easiest question that you have. It's like, yes, because they're the same number. That's all you have to have. Now, when you get to 15, okay, you got to go old school conversions, okay, of mole conversions. So 15 is mole conversion, 19 is mole conversion. And again, now that you have a better idea of these numbers, this is why I said don't ever, ever, ever tell me that the mass, when you're using Avogadro's number, that's 6.02 times 10 to the 23rd grams, okay? That's more than the mass of our moon, okay? So when you're doing mole conversions of mass, protons, electrons, neutrons are very, very small. This is why you never use 6.02 times 10 to the 23rd grams. You can use 6.02 times 10 to the 23rd atoms, 6.02 times 10 to the 23rd protons, but don't ever, 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 ever tell me that there's 1 mole is 6.02 times 10 to the 23rd grams. I am not going to have you go into that lab and measure out the mass of the moon and put it on a scale. It would be cool, don't get me wrong, but that's probably not what's going to happen. Okay, cool with this. Miles, let me get you what you need. And I'll send you this video, and you're just gonna need to like kind of watch that end of it. Okay, so studio audience can see this. So for now, I want you to get through page 11, stop at 19. Okay, so stop there. That's eventually we're going to work through this whole thing, but for now, we're going to take a break from this packet and stop at 19. Okay, so I'm going to give you the physics approach to this and not the chemistry approach to this, okay? So you end up with the same idea, but it's just a different way to get there. So if you look at, I'm going to give you two different equations, okay? And no, I'm never going to expect you to do any calculations with this. I'm just going to point out these two equations, because they form the heart and soul of what happens in physics. So this equation over here allows you to calculate the gravitational attraction between two objects, okay? So the big G is called the universal gravitational constant. Don't worry about it, it's a number. Do not worry about it, it's just a number, okay? It's just a number. The M's are the masses, okay? So like, for example, if I wanted to calculate the gravitational attraction between Izzy and Ella, okay? If I wanted to calculate the gravitational attraction between the two of you, all I'd have to know is your mass in kilograms, and how far apart you are. Now, here's what's important. It's divided by distance squared, okay? So this is why I passed around that ferrofluid. So as you increase the distance between the magnet and the ferrofluid, what happened to that attractive force between the magnet and the ferrofluid? Did it increase or decrease? Decrease, became weaker, right? So this is what's known as an inverse square law. There's a whole bunch of mathematical relationships that exist in science known as inverse square laws. Light intensity, gravitational fields, electric force, magnetic fields, a whole bunch of things work like this. So here's all I want you to get out of this equation, is that if you increase the distance between two objects, the gravitational force becomes weaker. Now, this is the equation that allows you to calculate either the repulsive or attractive force between two charged particles. So these Q's up here represent the amount of charge measured in coulombs. Do not worry about the numbers, just remember it's a certain amount of charge. And every electron and every proton has the same amount of charge, okay? I'm not going to expect you to do the calculations, just know that these are charges. And again, the K is just a number, don't worry about it, it's a number. Constant of proportionality, it's just a number. Then you're dividing by d squared. So here's what I want you to see, okay, out of this equation. As your charges get bigger, as you have more and more and more charge, the force becomes bigger because you're multiplying by a bigger number on top. If you alter the distance, as the distance gets bigger, the force becomes smaller. Okay? So here's all I want you to get out of this equation for now. Okay? If you increase the charge, okay, you increase the force because you're multiplying by a bigger number on top. If you increase the distance, you decrease the force. Okay? That's it. That's all I want you to see for now. Now, but because this is squared, okay, because this is squared, what that means is if you were to draw a graph of force and distance, okay, So there's 0, there's 0. So here's what I want you to think through. If we were to graph, like let's say for example, I've got these two particles. This might work. Problem is here is trying that. Hold that for a second. Oh, you kind of see those repelling. So what I did, I'll do this for those that are watching on DVD. So I've got two, I charged both of these balloons by rubbing them with a blanket. So this is the classic example. So as I bring these closer, what happens to the amount of repulsive force? I decrease the distance, the repulsive force becomes bigger. And the more I charge the balloons, the more I rub them with that blanket, that means I increase the, it's also attracted to me, okay, because I'm neutral. So what's happening is that this is attracting me because the chihuahuas are running away, but the other balloon is repulsed because they have excess chihuahuas, both of them do. So that little example is the manifestation of this. So here's my question. What would this graph look like? So if I were to plot the distance between the balloons, so when the distance is very small, is that going to be a big force or a small force? Emma,
What?
when I've got the balloons really close together, I have a small force. Is that going to be a small distance? Is that going to be a big force or a small force?
Big force.
Big force. As I increase the distance, what's going to happen to the force?
It's going to decrease.
It's going to decrease. So this graph is going to look something like this. Okay? And a gravitational attractive graph would look the exact same way. Okay? The exact same thing. So what this means is that as you increase the distance, the force becomes smaller. But as you increase the charge, though, if you were to look at force and charge, that's going to go like this. Okay? As you put more and more charge on it, the force becomes greater and greater and greater. But here's what you have to remember, and this is going to be important as you go through and you answer some of these questions. You're always going to change one or the other. Okay? You're either going to worry about, you're going to keep the charge the same, and you're going to alter the distance, or you're going to keep the distance the same, and you're going to alter the amount of force, or alter the charge. So here's what I want you to start to do. We're going to work through this whole thing. It's pretty straightforward, now that you have an idea. So what this is showing you here, what's up, Buttercup? Here, grab one of these. Okay. So what this is showing you, this model 1, is that they're keeping the positive charges the same, they're keeping the negative charges the same, and they're going from, and these are NM, that N stands for nano, which means 1 times 10 to the negative 9th, okay, which will be important later on, okay? So these are nanometers. It's just a measure of distance for now. So here's what I want you to see. As that distance goes from point 1 to point 2 to point 3, notice that the attractive force becomes bigger or smaller. Is it?
Smaller.
Smaller. You're dividing by a bigger number. So what's happening on model 1, if you go to this equation, on model 1, what they're doing is they're keeping the top part of this equation the same, and they're dividing by a bigger value of distance. Okay? Just keep that in mind. Mathematically, that's what they're doing. You don't have to do the calculations, but that's what's happening. Now, when you get over to page 3. Okay, so if you got this model 3. So what's happening there is that they're keeping the distance the same, but they're increasing the amount of charge. So on that one, the bottom number is staying the same. They're putting more and more charge on the system. So oddly enough, as you put more and more charge on the system, the force becomes bigger. So how this all plays out is, in terms of like chemistry and how things bond, is this on page 2. So what they're showing is that you have 3 different atoms. You have lithium, sodium, and you have potassium. So lithium has 1 valence electron, what we call a valence electron. So when I talk about a valence electron, what I'm talking about are electrons that are in the highest energy level away from the nucleus. So lithium has 1 electron, and what you'll notice is that here's this nucleus, and they've got, it's like a layer of an onion, okay? So the center is always the nucleus. That's where the protons and neutrons are hanging out. So what they're showing is that these little dots, and we'll figure out tomorrow how would they figure out how many dots there are. So if you look at lithium, there are 2 electrons in the first layer of the onion, okay? And that's all. You only put 2 electrons there. And then there's 1 electron out here, okay? So what's happening is that here you have that negatively charged electron, and here you have this positively charged nucleus. So what they're saying is that if you look at F equals K, Q1, Q2, over distance squared. So you've got 2 protons here that are pulling on that electron, and that's a certain distance away. So what you'll see mathematically, because that distance is squared, if you change the distance because that's a squared value, that makes more of a difference than if you change the amount of charge, because the charge is just multiplied together, but the distance is squared. So anytime, like if you double the distance, you decrease the force by a factor of 4. If you triple the distance, it goes down by a factor of 9, because it's d squared, okay? So what they're showing is that on these arrows, so then when you go to sodium, its 1 electron is like in the 3rd layer of the onion. The potassium, that electron is out there in the 4th layer of the onion. So what's happening is that you're making these distances get bigger and bigger and bigger. You're dividing by a bigger and bigger and bigger and bigger number. So therefore, that force is becoming smaller. So the width of the arrow that's what they're showing as the amount of force. So that lithium atom, that 1 lithium electron, which is pretty close to the nucleus, you're dividing by a pretty small number, that's a big force. Potassium, that electron is much further away, you're dividing by d squared, that attractive force becomes less. Okay, so that's what they're showing on that. So when you go through this, now you should be okay. So you should be able to go through the bottom of page 3. So what I want done by tomorrow is this packet completed, questions on the bottom of page 3. We'll finish this up in class tomorrow. So you should have enough information and knowledge to figure that out, and then we will talk more about that tomorrow. So, call it good. So, can you reach over and hit that silver button on the side and stop that camera?
Which one?
That silver button on the right side, on your right side, yeah.